Yeah, next I will give a talk on causal inference with instrumental variables. My name is Kuang from Zhejiang University. Here I would like to take 2 minutes to introduce the research interest of our lab. We know as just introduced by the Dr. Chao Lu, we know there are many spurious correlation in our data. Here we give some summarization on the source of correlation, including causation, confounding, and simple selection. And only the causation is stable or invariant across the environment, and the correlation is induced by the confounding bias or simple selection bias are always recalled as spurious correlation. So the first direction of our lab is can we use use the causal inference techniques to draw causation from big data? And the second direction is because we know the many good properties of the causation, for example, the stable or explainable or invariant. So we are thinking, can we use the causation to inspire or regularize the machine learning towards trustworthy machine learning methods? Okay, and today I will focus on the causal inference, how to draw causation from big data. Here we give an example. We know in our daily life, the predictive model, we have many predictive models, but does predictive models can help us to make a decision? For example, let's say we have two algorithms, algorithm A and algorithm B. We say the algorithm that is to provide the promotion or discount link to different customers. So if you are the manager, right, you are thinking, when should the system change the algorithm from A to B? That means we need to define which algorithm is better, right? So you may say, okay, let's do some experiment. For example, we let the algorithm to each algorithm have 1,000 customers, and we see the success rates of each algorithm, right? For example, we find during the 1,000 customers used with the algorithm A, we find 50 customers click the link or accept the promotion. That we say the success rates of algorithm A is 5%, right? And we find the algorithm B have 5.4% percentage success rate. Then we know the new algorithm, the algorithm B, increases overall success rate, right? So can we make a decision that the algorithm B is better than algorithm A? Maybe or maybe not. If we separate the 1,000 users into two groups, low-income users and high-income users, and you can find during the 1,000 users, the algorithm A has 400 from low-income users and 600 from high-income users. And for the low-income users, we can find the success rates of algorithm A is 2.5%, right? But for the new algorithm, the algorithm B, the success rate in the low-income users is only 2%, right? That means for the low-income user, the algorithm A is better than the algorithm B, right? Also, for the high-income users, we can have the same observations. That means the algorithm A is better than the algorithm B. But overall, if we see the overall, right, the algorithm B is better than algorithm A. Then, if you are the decision maker, right, how to make the decision? Which algorithm is better? Which algorithm should the system to change to, right? This two table just to show the correlation between some variables, and correlation actually cannot help us to make decision because correlation contains some spurious correlation. Actually, in our daily life, if we want to make some decision, the causal effect estimation is necessary. For example, in the medical field, if we want to release a new drug or a new medication, we need the experiments. We need to estimate the causal effects of the drug or of the medication. Because, for example, we might use the double-blind or triple-blind experiments, right? That means the triple bright experiment is help us to estimate causal effects of medication. In the social marketing, the marketer can easily decide whether to promote the social the campaign or the advertisement or not, based on the causal effects of the advertisement. In computer science, we say the experiment as the A/B testing, right? Actually, before we make a decision, if we have the opportunity, if we have the chance to do the causal estimation, I think it's a good choice. That means causal effect estimation plays an important role on decision making. Here we give a practical definition on the cause effects and the causal effect. We say T causes Y if and only if change T leads to a change in Y when keeping everything else constant. Then the causal effects can be defined as the magnitude by which Y is changed by a unit change in T, right? From the definition of the cause and effects, we find there are two key points to estimate the causal effect or to estimate the treatment effect. The first key point is we need to change the potential treatment or the potential cause. We say the variable T, right? The second is we need to keep everything else constant. Okay, here's the two key points to estimate the causal effect from data. Okay, here we introduce some notations. For example, if we want to estimate the causal effect or treatment effect from a new medication, here we use the variable T to denote the treatment. We use T equals 1 means the patient is taking the medication, and T equals 0 means not taking the medication. Then for each patient, we will have two potential outcomes. YT equals 1 means the outcome of taking the medication, and YT equals 0 means the outcome not without taking the medication. Right. Then based on the potential outcome, we can define the individual treatment effect and the average treatment effect by comparing the potential outcome or calculate their difference. From the definition of the treatment effect, we can find there is a counterfactual problem. That is, for each patient, for each unit, we can only observe one of two potential outcomes, right? One, YT equals 1 or YT equals 0. Only one of them, not both. To address this change or to address the counterfactual problem, and in our real application, if we want to estimate the causal effect, the gold standard approaches are randomized experiments. For example, if we want to estimate the causal effects of new medication, we can randomly select two groups of patients. Randomly select two groups of patients, and one is with the medication, the other is without the medication. Then we can compare the average outcome to estimate the average causal effects of the medication. From the randomized experiment actually satisfy the two key points or conditions of the causal effect estimation. First, the patients are randomly selected from population, right? This, as the number of patients increase to infinity, we can guarantee everything else are constant between the two groups, right? Then we have one group with medication and the other group without the medication. That means we have changed the treatment T, right? Although the random experiments are the gold standard approaches, but they also facing some drawbacks. The first drawback is the cost of money, cost of time. And the second is the problem from the aesthetic. In many real applications, we actually cannot do random experiments. For example, if we want to estimate the causal effect of smoking on the cancer, we cannot randomly select a group of people and let them to smoke for a month or for a year, right? So we are thinking, in big data scenario, in big data era, we have abundant observational data, right? So can we to can we do causal estimation with observational data? From the definition of the average treatment effect, we know we have to estimate the expectation of the potential outcome, right? But in observational data, actually we have units, we have samples with different treatment, right? Then we can calculate or we can estimate the expectation of each potential outcome, right? So can we estimate the ATE by directly comparing the average outcome between different treatment groups? Maybe if your data is from running experiments, so then you can estimate the ATE like this. But most of the time, the observational data are not from the random experiment, right? And if the data is not from the running experiment, we cannot do this because some variable, we say confounder, might not be constant between the groups. For example, if the medication is very expensive, right? Then the patients with high income can afford it and have high probability to take the medication. But for the low income user, they cannot pay for the medication, then they have no probability to take the medication. Then we can find the distribution of the income variable might be different between the two groups, right? Here we call the confounder. The confounder should be the common cause of the treatment and the outcome. And let us recall the two key points for causal estimation. First, we need to change T, right? In the observational data, we have units with difference T. So in the observational data, we can guarantee the first point is satisfied. But the second point is we need to keep everything else as constant, right? But in observational data, this point or this condition cannot be guaranteed. So the main change of the causal inference in observational data is how to balance the confounded distribution. To balance confounder, some researchers propose matching methods. For example, exact matching that match units with the same confounders. But these methods have poor performance in high-dimensional setting. Then Rubin proposed introduced the propensity score to summarize the information required to balance the confounder. And many approaches, many methods have been proposed based on the propensity score, including propensity score matching, inverse propensity weighting, and the double robust methods. But these methods may have some problems. The first is these methods treat all observed variables as confounders and ignore the non-confounders, such as the IV or the adjustment variables. And moreover, most of these methods are designed for binary treatment. In the computer science literature, there are also the representation learning-based methods are proposed for causal inference. The main idea of these methods is to learn the representation of the variables and make sure the representation between different groups are similar to guarantee the confounder is balanced between different groups. Then we can use the representation and the treatment to make a prediction on the factual outcome and the counterfactual outcome. And by comparing with the predicted factual and counterfactual outcome, we can estimate the treatment effect. Also, these methods also, did not consider the confounder differentiation. You know, in big data scenario, there are always a large number of observed variables, right? But not all of these variables are confounders. Moreover, not all confounders are observed. And in real application, the treatment variable are not always binary, right? So here we summarize some new changes for causal inference in big data era. The first is how to automatically separate or how to automatically select confounders for balance, right? The second is how to remove the bias from the unmeasured or unobserved confounders. And the third is how to deal with the continuous or complex treatment. To address this change, we propose several algorithms. For example, we propose data-driven variable decomposition algorithm to automatically separate confounders and several algorithms to adjust the continuous or the compressed treatment. Because of time limited, I will focus on how to adjust the unobserved confounding bias with instrumental variables. In the causal literature, one of the best way to adjust the unobserved confounders is instrumental variable-based methods. For example, the two-stage least square. If we can find a variable, we say z, that satisfies the conditions of IV, including relevance, exclusion, and unconfounded, then we can use the IV to help us estimate the causal effect or causal function between the treatments T and the outcome Y. Here we use the U to denote the unobserved confounders. Okay, here's the main idea of the two-stage least square. In the first stage, we can use the IVZ to regress the treatments T and obtain the predicted treatment, we say T hat. Okay. In the second stage, we can use the predicted T hat in the first stage, right, to regress the outcome Y and estimate the causal function or causal effects between the treatment and outcome Y. Here we show the two example to demonstrate the effective of the IV-based methods. Although IV can be applied to adjust the unconfoundedness, to adjust the bias from unobserved confounders, but IV-based methods require some strong assumptions and limited to linear setting. To break the limitation from the linear setting, recently many nonlinear IV regression methods have been proposed. For example, deep IV and kernel IV and so on. And these methods also adopt the observed confounders for two-stage regression. In the first stage, they propose to use the IVZ and the observed confounders. Here we use X to denote the observed confounders and U denotes the unobserved confounders. In the first stage, these methods propose to regress in T on IV and IVZ and observed confounders X. Okay, and also we can obtain the obtain the predicted treatment T hat, we say, right? In the second stage, they also propose to use the predicted treatment T hat and observed confounders X to regress Y and estimate causal effects with the regression function in the stage 2, right? But from the procedure of the nonlinear IV regression, we find the stage 1 regression might bring confounding bias in stage 2 if the regression model is misspecified in the stage 2. As shown in this figure, we know in the right figure, we know the X is the cause of the T hat, right? Because in the stage 1, we use X to predict the T hat, right? And we also know the X is the cause of Y in the causal graph, right? So before the regression in the stage 2, we know the X is still the confounder of the T hat and Y, right? So the stage 1 regression brings confounding bias in stage 2, and to adjust this change, we propose to combine the confounder balancing technologies with the IV regression and propose a very simple but effective algorithm we call as confounder balanced instrumental variable regression. In our CDIV algorithm or in our regression, we also have three steps. The first step is like the stage 1 in two-stage least square. We propose to use Z, the IVZ, and the observed confounder X to regress the treatment T and obtain the predicted treatment T hat. But before to do the second stage regression, we propose to actualize confounder balancing. We propose to learn a balanced confounder representation phi X from the X, such that T hat is independent with the phi X, right? Then we use the phi X and the T hat to predict or to regress the Y in the second stage, and estimates the causal effect or causal function with the regression model from the second stage. Because our algorithm is the combination of IV regression and the confounder balancing based methods. Here we compare our CV algorithm with the confounder balancing based methods and IV regression based methods. From the experiments, we can find our algorithm can achieve the best performance in different settings. Okay, here's the first work of our recent we published on the SML, and although IV can help to adjust the bias from the unobserved confounder, right? But all of these IV-based methods, they require a well predefined valid IV. It's always in practice in real application. In real application, we cannot, or it might take many time to find a well predefined valid IV. So we are thinking, can we relax the requirement on the well predefined IV? Here we consider a new setting. We say with the confounded IVs. We define the confounded IV as the invalid IV, which violates the unconfounded assumptions on the IV. Here we use T to denote the treatment, Y denotes outcome, X denotes the observed confounders, and the E denotes the unobserved confounders. Here we observe a set of invariant IV, Z1 to Zm. Z1 or Zi might be correlated, or might be the cause of E, or might be the effect of the E. Then in this setting, if the IV is not varied, the traditional IV method might fail in this setting. So, but here we need to assume during the varied IV or during the confounded IV, we have a subset of Z that are valid IV. We do need to know which variable is valid IV, but we need to assume during the set of Z, we have one or two or more are the valid IV. Then our goal is to estimate the individual causal effect. Okay, here is the key idea of our methods. We call as CVAE IV methods. The idea is to the algorithm is proposed to constructing the representation or substitute for the unobserved confounder. We propose to capture the information of the confounders from the unobserved E. Here is we propose a conditional independence criterion to run the representation or to run the substitute. The condition is we propose to run the representation E prime such that given E prime, T and X, Y should be independent with Z. Okay. Here we can say we can assume if some confounder information cannot be captured by our E prime, then given E prime Tx, Y would not be independent with Z, right? So with this conditional independence criterion, we can make sure all the information of confounders from E can be captured by our E prime. Here we want to emphasize is we need to recover. We are not to recover the E, but we only need to capture the information of the confounders from E. Okay, here's the details of our algorithm, and I would like to share the experimental results. Here we consider different settings, including the setting one. The Z is the effect of E, and here we have subset Z is the cause of E, and sub of them is the effect of E, and setting 3 is more complex. And during different settings, we can show our algorithm can achieve the best performance for estimate the causal effect. Okay. Moreover, in this work, we also need a path of predefined IV, although we don't know which IV is valid, right? So to to further relax the requirements of valid IW for IW methods, we propose to we are thinking, can we have a method? We have a representation learning algorithm to learn a representation, and the representation can be used to serve as the role of IW. So here we propose the algorithm to automatically to generate a representation to serve as the role of IW from the observed confounders. We use X to denote the observed confounders. U denotes the unobserved confounders. T is treatment, Y is outcome, right? So we propose the algorithm to decompose or learn disentangle representation from X and separate X into two subsets. One is Z and the other is C. So here we regularize Z to satisfy with the conditions of IW. For example, Z should be related with Z and Z should be independent with C. Then with the generating representation of Z, we can use Z as to serve as the role for IW and for IW regression. But here we need to emphasize that actually our algorithm cannot guarantee that Z is a valid IW because we cannot guarantee the second assumption, the exclusion assumption is satisfied. But from the experiments, we can find, although the generating IW representation might not be valid IW, but we find the experiments with the Z is comparable with the true IW. Okay, finally, I would like to take 2 minutes to introduce our survey paper on instrumental variable in causal inference and machine learning. In this survey paper, we categorize the existing IW-based methods into 3 groups, including 2-stage-based score, control function-based methods, and the evaluation on the on IW, including IW selection, IW evaluation, and IW synthetics. The main advance of both traditional statistical methods and machine learning enhanced methods are introduced and discussed. We also summarize the application of IW in many machine learning applications, including reinforcement learning and computer vision and recommendation. And we also developed toolkits of IW methods reviewed in our survey paper. Okay, that's all. Thanks. Is there any question from the audience? Okay, if no any question, or if you have any question, you can email me. If no any question, we might to move to the next session. Thanks.